This is Lab 5, Magnetic Braking with Faraday's Law by Suchit Munigati. So, the purpose of this lab was to observe a magnet falling through an aluminum foil cylinder and then comparing it with a computational model. And we wanted to see how Faraday's Law shows a generation of current. The three principles we'll be using in this lab are magnetic flux, which is just the amount of magnetic field passing through an area, Faraday's law, which is just the voltage with the time derivative of flux, and then Lenz's law, which is the induced current creating a magnetic field opposing the change in flux. So for the actual the physics model, the magnet creates a changing magnetic field at the ring, and the derivative flux dt with respect to time points downward, and then a cylinder with a cylinder, which is just an infinite amount of rings, so you can just use integration for that. It incorporates Lenz's law, which is just the magnetic field due to the in current pointing upward, and so this shows that the current and for this model the current is flowing counterclockwise, and then the magnetic force is just I times uh, the length cross B, and you can find B through the Biot-Savart law, which is uh, how you find it, and then it can be derived down to um, the current times 2 times pi times r times b times sine theta, which is that I times L cross B. So the actual experiment, uh, I recorded the physical properties of my aluminum foil, like the thickness, the length, and the inner radius, and then I dropped the magnet down the aluminum foil cylinder, and then I measured the time it took to reach the bottom. And so I a preview of the results, it averaged around 1.3 seconds, but the computation showed 0.33 seconds. And the reason we didn't use a ferrous tube was that it would interfere with the Faraday's law observations required for this experiment. So the measurements I took, the length was zero point 0.3 meters, the width was 0.005 meters, the inner radius of the tube was 0.025 meters, and the outer radius was 0.03 uh, meters, which was just the width and the inner radius added. The magnet's physical properties was that it was 0.023 kilograms, and then the magnetic moment is 2.1 amps. So here's my observations in a table format, and the average was 1.3 as shown. And so the magnet floats and it falls slower than in free space due to the upward force from aluminum, which is counteracting the downward force from gravity. So the top code segment is just the cylinder being modeled, and then the bottom is just the magnet being modeled. And the I calculate I filled in the formulas to calculate the B field from lab. The code was from lab 3, and then I also code coded the function for the d flux dt in GlowScript. And so the GlowScript portion of the code is just that the magnet is in the tube, and then when it is in the tube, you iterate through the rings to get the net magnetic force, and then you also find the magnet's acceleration and update the position and through that. And then we also plotted a position versus velocity time charts. And so the program's output in the black picture, the blue starts at the top and falls its way down, and as it does, it creates this velocity time graph and position time graph. So for the reflection questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Resistance and current are inversely related, so if the resistivity of the conductor was reduced as close as possible to zero, the current would grow, and as a result, the magnetic force would grow, and then the magnet would fall more slowly. If holes or slots were cut into the tube, uh, this would affect our model because essentially the cylinder would have less rings because there are holes at certain parts of the tube, and so there wouldn't be rings there. And so since there's less iterations, there'd be a weaker magnetic force, and then the magnet would fall faster since there isn't much of an upward force to counteract the downward force of gravity.